Good evening to all. Today we are going to discuss about thermodynamic process of constant pressure for real gas application. I'm sure this video is going to be very interesting. So please do keep watching until the end and subscribe my channel and don't forget to hit the bell icon. Thank you. So let's begin the discussion about thermodynamic process for constant pressure. Thermodynamic process, that is constant pressure, is also called isobaric process. And before that, let's understand the thermodynamic system. Thermodynamic system is defined as a system for uh, where heat transfer occurs, energy transfer occurs, and work transfer occurs. Let's understand with an example. A compressor does work on the gas and the gas energy increases. So here thermodynamic system is a gas. Similarly, not the compressor. Similarly, for high pressure energy gas produces power by expansion through the turbine. So here again turbine is not the thermodynamic system. It is the gas who does work. So whenever people say thermodynamic system, that means it is understood that it is a gas. Gas can be air, gas can be any hydrocarbon. So our focal point of discussion is only gas. So we'll see how the work done on the gas, how energy transfer increases, and how heat transfers occurs to the gas. So as per the sign convention, if the heat is transferred into the system, that means into the gas, it's considered positive, and when heat transfer occurs or it is taken from the system is considered negative. Similarly, when work is done by the gas or by the system is considered positive. When work is done on the system is considered negative. When the energy level increases, like gas does work on the when compressor does work on the gas, energy level increases where it is considered positive. When gas does work on the system, when gas does work through the turbine, then energy level decreases and it is considered negative. Types of thermodynamic system: it is open system, closed system, and isolated system. Open system, mass transfer occurs. You can see mass comes in and goes out, and also there is a energy transfer. In case of closed system, there is no mass transfer, only there is a change of energy or energy transfer occurs in the closed system. In case of isolated system, neither mass transfer occurs nor the energy transfer. Real gas equation of state can be written as PV is equal to Z nRUT. The only difference between ideal and real gas is the factor Z, that is compressibility factor. And so further we can define PV is equal to Z, and N can is a number of moles, can be written as a small m upon capital M, which is a small m is a mass, capital M is a mole weight, RU is universal gas constant, T is the temperature. So further we can rearrange P is equal to V by M is equal to Z RU by M into T. So further we can write V is equal to a small v is a specific volume, that is a meter cube per kg. So PV is equal to ZRT. This is a standard equation for real gas, and that can be used. Work transfer: in case of closed system, you can see the PV diagram. The area under the curve on x-axis is called the, or is equal to the work transfer. So work transfer is defined as a integration of PdV for the closed system. In case of open system, area under the curve on y-axis, that is on pressure axis on PV diagram, is considered as a open system. So area, it is equal to work transfer for the open system, and as per formula it is written as minus VdP. Work done by the system as per the sign convention is positive. Work done by the on the system is negative. This is true for both open and closed system. This is as per sign convention. And work transfer per unit mass is called the work head or head. Energy transfer. Energy transfer for the closed system is equal to internal energy change, and internal energy change is equal to integration of CVDT. So energy transfer for the closed system can be written as integration of CVDT. Similarly, energy transfer for the open system is called to enthalpy change, and enthalpy change is written as integration of CPDT. So energy transfer for the open system is equal to integration of CPDT. These are a standard formula that you need to use. And if the energy of system increases, it is considered positive as per sign convention. If energy of system decreases, it is considered negative. This is again, it is as per the sign convention. As per the first law of thermodynamics, heat transfer is equal to work transfer plus energy transfer, because energy is, so Q is equal to W plus E. But most important assumption is that as per the first law of thermodynamics, efficiency of thermodynamic machine is 100%. That means there is no losses during the transfer of work, transfer of energy, and or transfer of the heat. So process is ideal. Efficiency of machines are 100%. With that assumptions, first law of thermodynamics uses Q is equal to W plus E. So through using this equation, you can calculate the heat transfer. Now the constant pressure, as I said, it is also called isobaric process, which is shown on the PV diagram and TS diagram. PV diagram, the process pressure is constant. So you can see 1 and 2 process when heat is given to the system. Similarly, 1 and 2 is heat is removed. So 1 and 2 on the TS diagram, in temperature increases, entropy increases. Signal below this 1 and 2, heat is removed, so temperature drops, entropy drops. Work transfer for the closed system, we can write PV diagram. You see the area under the curve on x-axis is the work transfer, which can be derived. P is a constant, so PV is integration of P dV. P is constant, so write P1. V2 minus V1, so P1 V1 is equal to V2 by V1 minus 1. PV1 is equal to, we can use this PV is equal to ZRT. P1 B1 is Z1 RT1, and P2 V2 is Z2 R2. Using this equation, you can write W is equal to Z1 RT1 bracket start V2 by V1 minus 1. So this is the work transfer equation for constant pressure process in closed system per unit mass. For total mass, just multiply M with this. This will give the total mass work transfer. Then energy transfer, as you know, the CVDT, integration of CVDT. So CV into T2 minus T1. This is the energy transfer per unit mass. For total, you have to multiply M. As for first law of thermodynamics, you have to add both. So you can find heat transfer Q is equal to W plus E. You can write this is equation for W, this is equation for E. You just add up. So this is the equation for heat transfer per unit mass. For the total mass, just multiply M into this equation. This will give the total heat transfer. And heat transfer is also shown on the area under the curve on the x-axis on TS diagram. So S is on x-axis. You can see this is equal to the heat transfer. Now, open system, constant pressure process in the open system. PV diagram you can see as per open system, area under the curve on y-axis. Here you can see this is 0. That is why work transfer is 0, and this is also true as per using this equation. W is equal to minus V dP. There is no change in P, that is why it's 0. So we can say the work transfer in case of constant pressure in open system is 0. So total mass is also 0. Total mass for work transfer is all 0. Now energy transfer, you can CPDT, because for the open system enthalpy change, so you can write Cp T2 minus T1. This is for the per unit mass. For total mass, you have to multiply M into E, that is M Cp T2 minus T1. Again, as for the first law of thermodynamics, you have to add W plus E. W is 0 for open system. So Q is equal to Cp T2 minus T1. So you can write Cp T2 minus T1. So to heat transfer per unit mass is Cp T2 minus T1. For total, you have to just multiply M. Total heat transfer, just multiply with mass M. And you can see the area under the curve on TS diagram on x-axis. This will give the heat transfer. So this is heat transfer in the open system for the constant pressure process. Now let's understand with an example for the open and closed system for the constant pressure process. Nitrogen gas has initial pressure and temperature are 0.5 bar gauge and 30 degrees Celsius respectively. Heat is added to the thermodynamic system such that the final temperature reaches to 90 degrees Celsius on constant pressure process with consideration of real gas. Calculate work, energy transfer and heat transfer during this process for considering the closed and open system. Also, calculate the inlet and outlet specific volume. Following data are given. Mole weight of nitrogen 28 kg per kilomole. Universal gas constant 8314.5 joule per kilomole per Kelvin. Specific heat capacity at constant volume and constant pressures. Both are given. Are 20.88 kilojoule per kilomole and 29.25 kilojoule per kilomole respectively. Compressibility factor at inlet and final condition are 0.999 constant and 1 respectively, and local barometric pressure is 1 bar absolute. So this is the question. Now we have to find all the information for closed and open system. This is for the closed system. Barometric pressure is given. Absolute temperature is already we know 273.15. So inlet pressure, just add the gauge plus this barometric local pressure. It is 1.5. Inlet temperature 30 degrees Celsius. Outlet temperature 90 degree. Mole weight Z1 Z2 are given. CV CP both are given. RU universal gas constant it is there. Now calculate gas constant R is equal to RU by M. We can calculate then CP is also calculated. Just converting, joule per kg per Kelvin. So we have to multiply 1000 divided by molecular weight. So it will convert joule per kg per Kelvin for CP. Just divide to will get the K value. Cp by Cv, and inlet specific volume V1 is equal to Z1 R T1 upon P1. Just multiply 10 to the power 5 because we have to convert units are in bar, so we have to convert in Pascal. So it is coming zero point 0.6, and also calculate the V2 using this equation. See, this is 0.719, and work transfer using this equation Z1 RT1 bracket start V2 by V1 minus 1 bracket close, it is coming 17,907 joule per kg, and energy transfer CV into T2 minus T1 is 44,743, and heat transfer, just add these two, it is coming 62,650 joule per kg. This is for the closed system. And for the open system, there will be only change in the work transfer, energy transfer, and heat transfer for the open system. So just calculate only three. Work transfer is 0. Energy transfer is 62,679. This is CP T2 minus T1. And this is equal to also heat transfer because work transfer is 0. The same thing, 62,679. So I hope you have enjoyed this session. Thank you. Thank you for watching.